In this lecture, I will discuss binary codes. As you know that human being understood decimal digits, but computers internal representation is in the form of binary codes. There are several types of binary codes that are developed time to time. To understand binary codes, let us take 4 digit 0, 1, 2, 3, 4. There are 4 distinct digits. To represent it, we have to use only 2 bit 0, 0, 0, 1, 1, 0, 1, 1. So 4 distinct number that can be represented by 2 bit codes. Therefore, this is a set of 2 bit strings, and this is a binary codes. For example, representation of various types of other codes. For example, octal digit. Octal digits is from 0 to 7. We have to use 3-bit code here, and this is known as a binary code words or binary pattern strings. If there are 4 different elements, we have to require 2 bit. If there is 8 different elements, for example, here in octal system there are 8 different elements or symbols, we require 3 bits. Therefore, there is a relations between the number of bits and the total number of symbols or total number of elements that needs to be encoded. So here is 8 different elements, so we use 3 bit. And similarly, if there is if we use hexadecimal systems, there are 16 different symbol, and we have to use 4 bit. So there is a relation between the number of bits and the number of elements in the group, and this is related as 2 to the power n. N-bit binary code, a group of n bit that can be encoded up to 2 to the power n distinct elements. And here 2 to the power 4 is equal to 16, that is for hexadecimal system. Similarly, 2 to the power 3 is equal to 8, that is for octal system, and so on. But there is the maximum number of elements that is encoded by n bit is 2 to the power n. We can, if we have, suppose that we have to encode only 9 or 10 digits, then we have to require 4 bit. But using 4 bit, we will encode 16 elements, but here it is only 10 elements. That is used in decimal number system. Non-numeric binary code, that means that is not used for calculations work, arithmetical calculation works. For example, to represent colors, here is there is 7 colors. 7 colors is represented with 3 different bits. In this way, if there are m distinct element, we have an n bit code, then 2 to the power n is greater than or equal to m. That means we will encode m distinct element, maximum of m distinct element. If there is 2 to the power n is the maximum limit, then we have only encode m distinct element, where m distinct element is less than or equal to 2 to the power n. For example, here total number of element is 7, but if we encode here, then it will encode 8. So 7 is less than or equal to 8. So if there is m distinct element, we can and with an n bit code, then 2 to the power n is greater than m. That means m distinct element should be less than or equal to 2 to the power n. There is different type of binary codes to represent number and characters apart from the conventional binary systems. First is BCD code. BCD means binary coded decimals. It is used for arithmetical calculations. Another codes are EBCDIC code, that is developed by IBM company. It is a 8-bit code for 256 characters. It is a character code. ASCII is used nowadays. ASCII is a popular code and it is used in most of the computers. EBCDIC code is only used by IBM companies. ASCII means American Standard Code for Information Interchange. It is a 7-bit code. Next is Unicode. Unicode Unicode represent various other languages, for example English, Hindi, Russians, any type of characters. That means non-Latin based alphabetic characters is represented by Unicode, and it is a 16-bit code and it allows 65,000 plus characters. How to 16-bit allows 65,000 characters? Simple. 2 to the power 16 is equal to something 65,553. So it can encode 65,000 characters. How binary coded decimal is represented? Binary coded decimals, there is a table 0 to 9, the BCD representations. 0000 4-bit codes. These are 001, 01, 0010, 0011, 0100, 0101 and so on. But here 1010 and 1 to up to 1111, that means 10 to 15 is not used for BCD codes. They are invalid codes. For example, some digits here, some numbers here. For example, 35. How 35 is represented in BCD? The BCD code is 0011 and 5 is 0101. So the 35 is represented as 00110101. Similarly, 98 is represented here. Write the code of 9 and write a code of 8, then it become 98. Similarly, 170, replace 1 with binary code 0001 and 7 is 0111, 0 is 000. In this way, we can use BCD codes to represent different types of numbers, and it is easy to represent this and calculations work in the computer system. Similarly, we can convert the BCD code into decimal number system. Very simple. Replace the code with the required digits and you get the BCD to decimal conversion. BCD additions. Add two BCD numbers using the rules for binary additions. If a 4-bit sum is equal or less than 9, it is a valid BCD number. Since 9 from 0 to 9 is a valid BCD number, so if the sum is less than or equal to 9, then it is valid BCD numbers. If a 4-bit sum is greater than 9, or if carry out of 4-bit group is generated, it is an invalid result. Then add 6 to the 4-bit sum in order to skip the 6 invalid states and return to the code to 8421. Actually, BCD code is also called 8421 code. If a carry results when 6 is added, simply add the carry to the next 4-bit group. We'll see some example. Add the following BCD numbers: 0011 plus 0100. When it is added, 3 plus 4 is equal to 7. 7 is a valid BCD code, so further processing is not needed. Here 23 plus 15, that is 38 binary coded values. It is simple binary additions. Then it becomes 38. Now here 450 plus 417, it becomes 867. Again it is a valid binary code. BCD addition. In BCD addition, the maximum symbol to be accepted is 9. If it is greater than 9, then 6 is added. For example, here 001 plus 0100, that means 9 plus 4, that is 13. In binary, 13 is represented as 1101. 13 is not accepted in BCD code, so add 6 is added, that is 0100 is added. After adding 0100, it becomes it is simple binary additions. We make simple binary addition here, and it become 0001, and second part is 0011. So this is 1 and this is 3. Finally, this is 13. Hence, if the number is greater than 9, then 6 is added to the result. Similarly, in the case of second number, that is 9 plus 9, 18. 18 means here is added. If we perform binary addition, it become 10010. So 18 is not a valid symbol. 6 is added here. 6, after adding 6, it becomes 1 and 8. In this way, rest the numbers is added. Here in the example D, the number is 0100 and 011, that is 67. This is 6 and this is 7. This is 67 plus 53. It will be 3. It will become 120. But when we perform binary addition, it become 1011 and 1010. Both group are invalid, since this is greater than 9, this is also greater than 9. So in both the cases, 6 is added. Now perform the simple binary additions operations, and it after adding the two number 1010 and 0110, it becomes 0000, and the carry is if carry remain, then it is forwarded to next part, and it becomes 0010, and next is carry forwarded, that is 0011. Ultimately this become 1, 2 and 0, which is a valid BCD number. Another code that is used for calculations for numeric code, that is XS3 code. XS3 code means BCD, it is added 0011, that is 3 is added to BCD code, then it become XS BCD code. For example, 0010 is equal to 2 in BCD. When 0011 is added, then it becomes 0101, that means 2. Then in XS3 BCD code, 2 is represented at 0101. It is also known as 2421 code. For example, decimal 0, then it is 0000, but when 3 is added, it becomes 0011. Similarly, in other numbers, in decimal numbers, with the BCD code, 3 is added, and finally it become, in case of 9, if 3 is added, then it is 12. Therefore, in XS3 code, the total binary symbols are started from 3, and its last binary code is 1100. When, for example, 1, if it is in BCD code, then it become added to 3, and 4 is its XS3 code. If it is 3, then 3 is added, and it is become 6. Similarly, 430 is a BCD code. 430 is a decimal number. Its BCD code its XS3 codes is represented as 763. So 7 is represented as 011, 6 is represented as 0110, and 3 is represented at 0011. Another popular code which is overall accepted, universally accepted, is known as ASCII code. ASCII code means American Standard Code for Information Interchange. It is alphanumeric codes. In the keyboard there are total 128, total of 108 keys. That is 26 uppercase, 26 lowercase, 10 GD, 32 special case, and 34 non-printable control functions. Total 128 characters are there. To represent 128 characters, we need 7 bits. Since 2 to the power 7 is equal to 128, and in ASCII, so ASCII is a 7-bit code, and 1 bit is added as parity bit for error detections. This is ASCII table. ASCII table, this various type of characters. Here the least significant bit B1, B2, B3, B4, and here B7, B6, B5. To determine null character, we have to select 0000, and from here 000. To select DLE, the 0000, and last is 0001. Similarly, any characters is selected from the matrix is represented as, for example, ESC. ESC is a key. Then its ASCII value is 1011, and here from 0001. Therefore, from row we can write 1011, and from column it is 001. Total its ASCII code will be 1011001. In this way, we can determine the ASCII value of the different characters. Here A is a character, uppercase character. Its ASCII value will be 0001, and from here 100, and so on. Another code is Unicode. Unicode is represented by 16-bit alphanumeric codes. In a Unicode system, we can represent any non-Latin characters, for example Hindi, Bengali, Urdu, any type of characters. It is universally accepted code, Unicode. Now, parity bit checking. Since when data transmitted from one place to another in the form of bits, the bit may be changes. For example, 1 is changed to 0, 0 is changes to 1. Then the informations may make a problem. There will be errors in the informations. how errors can be determined. One of the method is parity bit. How parity bit checks the errors we will see in the next slide. There are two types of parity bit checking. First is even parity, second is odd parity. Even parity means the number of one must be even, total number of ones must be even, and odd parity means the total number of one must be odd. Parity bit means a single extra bit is added in the data word. The new data word is transmitted. In the receiving end, again it is checked. If there is any error, then it is detected. We will see in the next slides. Here there is parity, even parity and odd parity bit. For example, 0000, this is a BCD number and its even parity is 0. Similarly, here 0001, that means 1, its even parity is 1. Since total number of ones is even. So 1 is if even parity, if 1 is added, then it has a even number of ones. Similarly, 0010, its even parity is 1. Since total number of 1 is even. Here even parity is 0. Since already it has even number of ones, so only 0 is added here. And so on. For example, here there are 3 ones, and to make the number even, 1 is added. Bit 1 is added, and it become even number of ones. What has happened if we XOR all the even parity, all the ones, we get the XOR value is equal to 1. This is the main objective of even parity, and to implement even parity or parity, we use the XOR gate to check whether it is even parity or odd parity. In odd parity, what has happened? That even there will be the odd number of ones. For example, if BCD is equal to 0000, then we have to add 1 and it become odd parity. Here it is 0, since already 1 is present there. Now in the here 0011, there is even parity, even number of ones, and 1 is added, then it become odd parity. How error is detected? A parity bit provides for the detection of single bit error, but cannot check for 2 errors in one group. For instance, let us assume that we wish to transmit BCD code 0101. The total code transmitted including even parity is even parity is added here only 0, since there are already 2 ones present here, so even parity is 0. Let us assume that an error occurs in the third bit. For example, here 1 is inverted to 0, that means it's bit in error. The 1 becomes a 0. In the receiving end, the even parity is checked, and it found that it is 1, but in the when it is transmitted, it is 0. So because an even number of ones does not appear in the code when it is received, an error is indicated. In this way, the error is determined. In this way, we can generate ASCII parity bit. In the ASCII parity, there is 7-bit ASCII code and 1 parity bit is added. Here also even odd parity can be generated. For example, the make 7-bit code 10111011, there is 5 1 already present. So 8-bit even parity code and one extra 1 is added here, and it become even parity. Similarly, the make 7-bit code 1011, the odd parity will be 0. Another is gray code. Gray code is very useful in circuit designing and networking and genetic algorithm. It was invented by Frank Gray in Bell Labs by reflected binary code in the 1947 patent application, remarking that the code has as yet no recognized name. The Gray code is named as per the inventor Frank Gray. This is the mirror. This is the reflections binary code, is represented by the figure. What is gray code? The gray code is unweighted and is not an alphanumeric code, arithmetic code. That is, there are no specific weights assigned to the bit positions. The important feature of gray code, it exhibits only a single bit change from one code word to next in the sequence. For example, decimal number is 0, the binary is 0000, and gray code is also 000. In this way, binary is 001 and here 0001. Both are same, but here 0010, 2 is represented as 0010, but in gray code it is represented as 0011. From 1 to 2, here there is 2 bit changes. The first, in binary number system, there is 2 bit changes, that is 1 inverted to 0 and 0 is inverted to 1. But here 1 remain the same, that is least significant bit remain the same, but the next bit is inverted to 0 to 1. So in the case of circuit designing, it is simple task for the flip-flops to invert a single bit, and it takes a lesser amount of time. In the case of binary numbers, it takes large time. First invert the least significant bit, and then next bit is inverted. So a 2 unit of time. In the case of, it takes 1 unit of time. So the circuit, the timing is minimized. Similarly, error detections is not also a problem when one bit is changes to another. 1 bit error detection is very easy task. So gray code is also used as in the sequencing of network informations. When a set of bits is sent from one source to destinations in the form of gray code, it is easy to determine the bit sequence and bits that are in error. Similarly, other numbers can be generated through the gray code. You can find here each from 0 to 1 there is 1 bit changes. From 1 to 2 there is 1 bit changes. 2 to 3 there is again 1 bit changes. Here from 3 to 4 there is only 1 bit changes. In the case of gray code, it is a very simple task, and the circuits require lesser amount of time. This is techniques to find the gray code for a particular binary code. The most significant bit, the leftmost in the gray code, is the same. It is the leftmost bit, it remains the same. Going from left to right, add each adjacent pairs of binary code bits to get the next gray code. Discard the carry. For example, this is a binary code 10110, and the first bit is written as it is, and next bit is added to 0, it become 1. Then 0 is added to 1, it becomes again 1. Now 1 is added to 1 and carry is discarded. If carry is discarded, then its value is 0. Then 1 is added to 0, it become 1. So the gray code will be 1 1 1 0 1. So binary code, if the binary code is 1 0 1 1 0, then its gray code will be 1 1 1 0 1. Similarly, we can convert a gray code to binary code. Its calculations is follows. The most significant bit leftmost in the binary code is the same. Here 1 is remained the same. Add each binary code to generate the gray code bit in the next adjacent positions and discard the carries. For example, this is a gray code. Now this code, this bit is added to this binary gray code and it becomes 0, and this 0 is added to this gray code and this becomes 0. In this way the process goes on. Now the gray code, if the gray code is 1 1 0 1 1, the binary code is 1 0 0 1 0. Similarly, there are several examples to convert a binary code to gray code and gray code to binary code. The principle is the same. This is all about the digital codes. Thank you.